Now for something slightly different, but totally new. Consider this. After this point in the first 4 chapters, we've been studying motion, the empirical study of motion, just looking at motion, trying to fit equations that describe the motion. We call this kinematics, the study of motion, purely empirical. But at some point, we're interested in the cause of motion. What is behind it? What is creating these equations? And that is dynamics, the cause of motion, and most importantly, forces. Forces are the cause of motion. So we are about to look at dynamics. Let's define some forces. Contact force. Contact force is a force that acts through physical contact. It could be something like this. You have an object, and you come in and you touch that object and you push that object, and the object moves as a result of your physical contact with the object. There are other kinds of forces. Field forces, forces which seem to act through empty space. Examples: gravity, gravitational force. You have the planets attracted to the sun, and there seems to be a gravitational force through empty space that keeps the planets bound to the sun, that keeps stars bounded to galaxies and that sort of thing. Electric forces between positive and negative charges. There is a force that acts at a distance, which seems to be through empty space, even though there's a field involved, and hence we have a force from a distance through empty space. Magnetic forces, the same thing. They're magnetic fields, even though you can't see them. They seem to act and cause magnetic forces on objects. And nuclear forces. Nuclear forces acting on the nuclear level, inside the nucleus itself. The strong nuclear force acts at a very limited distance, very strong force. So these are 4 main forces, field forces, we can identify. You know, about 100 years ago, at the turn of the 20th century, there was really about 7 forces on this list. 7 basic forces identified in nature, including things like the van der Waals force, the strong nuclear force, the weak nuclear force. All these forces were the forces that were on the list. And as the physicists and the theorists started putting things together, they started combining these forces within the theory, and they were able to pretty much narrow this down to 3 main forces. You have the gravity force, you have the nuclear force, and the electromagnetic force. So the electric force and the magnetic force are really just one force. If you change an electric field, you get a magnetic field. If you change a magnetic field, you get an electric field. So they're really intertwined. They are one force, electromagnetic force. And really, after a little bit of theoretical work, there were 3 main forces in the universe identified as gravity, electromagnetic, and nuclear. Einstein continued to work throughout his life trying to unify these forces into one unified force. Was not able to do it before the end of his life. But if you believe in string theory, the idea that there are little strings on the order of so small, 10 to the minus 40 meters, that you might not be able to ever discern them, you can actually combine these forces into one unified force. So that is the purpose of modern theoretical physics, is to try to combine these forces into one unified force in the universe. Another point, we mentioned contact forces, and I didn't put that on the list as I'm talking about these basic forces, because really there is no such thing, at least on the atomic level, as a true contact force. If you go on the atomic level and you study the contact between one object and another object like this, you will find that, say in this case, my atoms don't actually touch the atoms of this apple. On the nuclear or on the atomic scale, the outer electrons in the molecules of my atoms have electromagnetic repulsion with the outer electrons on the molecules of this apple, and that matter never actually touches. It's the electromagnetic force at that level that repulses, and that causes the force of touch. So in a sense, I never really touched this apple. And so there's no such thing as, in truly sense, as a contact force. You could probably put this to your advantage. Say you were the witness for the defense in a trial. Your client's been accused of stealing $2 million. And they call you up on the stand and you say, I know you say that my client put his hands on the $2 million, but in reality there's no way my client could have touched that money, because in physics there's really no such thing as a contact force. The molecules of his hand never actually touched the molecules of that $2 million. So since there's a shadow of doubt, you have to let my client go free. Just make sure if you do this that your client actually stole the $2 million so that they can pay your $1 million fee for you compromising your morals and defending an obviously guilty person. So think about that. Could make you some money. Sir Isaac Newton, 1642 is when he was born, the same year that Galileo died. So in a sense, the spirit of science was passed from one great genius to another great genius in that year, 1642. Isaac Newton devised the basic concepts of motion, the motion that we're looking at in this course, invented calculus along with Leibniz. So there's some argument as to who actually invented it, but they did it simultaneously. We'll give it to Newton in this discussion. Explain the gravitational effects of Moon and the Earth. Devised the universal law of gravitation, which we'll look at later in this course. Invented the Newtonian or reflecting telescope. It's actually a better design than the refracting telescope that you often see, but all the major telescopes used today, the Hubble telescope, all the large telescopes used today to look at the universe are really based on the design of the Newtonian telescope, the reflecting telescope. Showed the spectral nature of white light, showed that white light was composed of many colors, many frequencies. All this was published in one grand book called the Principia, Mathematical Principles of Natural Philosophy. In 1687, Newton did it at the age of 45. And he really did it all on his own. There really wasn't a chance for him to bounce ideas off peers and get some feedback. He really did this all on his own. Brilliant book, brilliant masterpiece, and really shows you how what a great scientist Newton was. How could he do this? How could anyone do this on their own? It's just unfathomable. And if you can say that word. And one way that Newton could do it is he actually worked in the mint. So he had a pretty good job. Anytime he needed some money, he could just print out a few more dollar bills, put his face on it, print those out, pay whatever bills he had, and then go back in the back room and work on some more physics. So pretty good to have that kind of job. Here's Newton's first law. An object at rest remains at rest, or an object in motion continues in motion in a constant straight line velocity unless it experiences a net external force. So what he's saying is the natural way of things is if an object's at rest, it will remain at rest. Or if an object's already in motion, moving in constant straight line velocity, it will remain in constant straight line velocity forever and ever and ever unless there's a net force on it. All right. So in the case of a rest or a constant straight line motion, there could be forces on it. In this case, there's gravity pulling this down. There's my hand pushing it back up. There are forces on it, but those forces are canceling out in terms of magnitude and direction, and so the net force on it is zero. Same action is if you went out and you had a buddy out in space and you gave your buddy a push, your buddy would go forever and ever and ever with no net force on him or her. And you would see that Newton's first law was actually in effect, as you could travel great distances without any extra thrust. So do that next time you're out in space. You might enjoy that. Your buddy won't enjoy it, but you might. That's how NASA sends probes to different planets. The main thing is trying to get enough thrust to escape the Earth's gravity. And once you get past Earth's gravity, then you just give it a little push and let it go. And traveling through space, you don't need any extra thrust. There's no resistance. And so it's Newton's first law of traveling at straight line velocity forever and ever and ever until you get caught by the gravity of another planet. The reverse of this is true. Constant speed means no net force. So if you see something moving at constant speed in a straight line velocity, then you can conclude that even though there might be forces on that object, they're all canceling out in whatever direction. So that means you can say that the net force, if you add them all up, would add up to 0. That's kind of interesting. So if you're driving down the road at 55 miles per hour in straight line, constant velocity, the net force on you is 0 at that moment. So whatever the engine is supplying, propelling you down the road, and whatever friction in the air and on the road is working against you, your net force is 0 at that moment. If an object's at rest or moving with constant velocity, then it's true that if you did sum up all the components of the forces, say in one direction, like the x direction, positive or negative, if you sum up all those forces that are acting on the object, they should add up to 0. This is just a mathematical statement of what we just said for Newton's first law. If it's at rest or moving at constant velocity, the sum of all the components in any direction should be 0. And that would be true for the x direction, that would be true for the y direction, and that would be true for the z direction, or any direction you chose. If there's no net force on it, it doesn't matter which direction you choose, you add up those components of the forces at that moment, and they should add up to 0, at least in a vector sense. This is the mathematical basis of statics. If I see something that is static at rest, there could be forces on it, and maybe I know a bunch of those forces. Maybe I know what gravity is. Maybe I know what the normal force is. Maybe I know all these forces, and maybe there's one force I don't know. So I can add up all the other forces, and based on those forces, they should be balanced by the one force I don't know, because it should add up to 0. So then I can find out what that last force actually is. And that is really the way that statics works. Mass. Mass measures inertia. And inertia was defined by Galileo as the nature of an object to resist changes in its motion. It's an inherent property of everything. Everything has a certain amount of mass, and it's inherent to that object, no matter where that object happens to be. So if this apple has mass, and it has the same mass whether it's in Earth's gravitational field here, or whether it's in the moon's gravitational field, or whether it's out in space. Everything has a certain amount of mass, and associated with that is a certain amount of inertia, the resistance of an object to changes in its motion. It's different from weight. This apple has a certain amount of weight because we're in Earth's gravitational field. If it's out in space, it could be weightless because there's no gravity, no gravitational acceleration. But it would still have the same mass. Based on this, let's talk about a seatbelt locking mechanism. Here we have a seatbelt locking mechanism. We can see that the belt goes through a shoulder harness here, goes to a ratchet, and then we have a mass connected to a latch. And if you had to stop suddenly, that mass, which might be on a rail type system, is going to continue to move forward because of inertia. And so as it moves forward, based on this property, the latch will come down and engage the ratchet, stop the ratchet from moving. engage your seatbelt harness, and it will hold you in. So you don't have to do any thinking. This is something that would happen automatically as part of this mechanism. And without thinking, then the seatbelt will lock and hold you in place. So in a sense, you actually trust in physics your life, because you are counting on the fact that such a mechanism like this, which is based on the properties of mass, will act properly under the right circumstances in the future, so that if you did get in an accident, the seatbelt will lock and hold you in place. Newton's second law. The net force on an object is directly proportional to its mass and directly proportional to its acceleration. We state it in vector form like this. The net force as a vector is equal to the mass, a scalar, times the acceleration, a vector. F equals ma. It is probably the most famous equation in physics, or even in science. Years from now, if somebody comes up to you and says, you know, you took that physics course, did you learn anything? And you will say, yeah, I learned F equals ma. It's the most famous equation, Newton's second law, describing forces. Force and acceleration go together. You know, when we were talking about acceleration earlier with kinematics, we said one way to intuitively know that you're being accelerated is that you'll feel force. You know, if I put my foot on the accelerator of my car, and at that moment I'm pushed against the seat, and even though my car may not have started to move yet, it might still be zero velocity, I know that there's an acceleration because I'm pushed against the seat. So the force is associated with an acceleration, and they go together. They're proportional by your mass. So the mass is just a scalar constant. The unit of force is a kilogram meter per second squared. So it goes with mass and acceleration. Kilogram meter per second squared. And this is used so often in the SI system that there is a unit assigned to that called, coincidentally, the Newton. Who would figure? So the Newton is a kilogram meter per second squared. And the weight of a small apple, maybe like this, is approximately 1 Newton. So in one fell swoop, when the apple fell on Newton's head, not only did he discover gravity, but he also discovered the Newton. The Newton. Yeah. Also, coincidentally, the weight of a package of apple Newtons is approximately 1 Newton as well. How about that? It kind of kills two birds with one stone, the apple and the Newton. I used to say fig Newtons was a weight of about 1 Newton, but I actually weighed one of these things. Fig Newtons are a little bit bigger than the apple Newton package, and it actually weighs closer to 2 Newtons, so I can't use fig Newtons. But apple Newtons is even better, so we'll use that. And they get smaller and smaller as the economy gets a little bit rougher. So this second law of Newton, this F equals ma, can be broken down from a vector equation into scalar-like equations in the x, y, and z directions. So if we sum up all the forces in the x direction, and we actually come up with some kind of net force, we will end up with mass times the acceleration in the x direction. If we summed up all the components of forces in the y direction, that should add up to mass times the net acceleration in the y direction. Same thing for the z direction, same thing for any direction you choose. If there is a net force in your direction, and you sum up all those components and come up with that net force, that should equal the mass times the acceleration in that direction. This is just the scalar component form of Newton's second law. You can see by this also that if you happen to be static at rest or moving at constant velocity, your acceleration will be 0. And hence, in this equation, if your acceleration were 0, all these acceleration values would be 0, and the sum up of all the forces would be 0, and you would have Newton's first law. So Newton's first law is a subset of Newton's second law for the special case where you have no acceleration. Acceleration 0, all the net forces add up to 0. Newton's third law, we're going to state it like this. For every action, there's an equal and opposite reaction. Say you had a ram and another ram and they're butting heads. If one ram exerts a force on the first ram, the first ram will exert a force back, equal and opposite, equal in magnitude, opposite in direction. These forces will have the same magnitude but opposite directions. For every action, there's an equal and opposite reaction. So I say that the force that 1 exerts on 2 is equal to the negative of the force that 2 exerts on 1. This is true for every force pair that we have in the universe. Every time two objects exert a force on each other, equal and opposite. If I were a boxer and I punch somebody in the face, I exert a force on their face exerts the same force on my hand. So I get the same punishment back. Of course, it's on my hand, not my face or my jaw, but it's the same force back on me. If I'm a large running back in an NFL team, and I start hitting the linebackers and defensive backs on my way to running for a touchdown, every contact I make, every force that I exert on somebody else is actually exerted back on me too. So that punishment that I'm dishing out is also coming back on me, and that's why a lot of these running backs get pretty well beat up over the course of their career. This action-reaction pair still exists even if you make contact with a stationary wall. Let's say you've been working on the unified field theory for most of your life and you just can't figure it out, and you get pretty frustrated and you bang your head against the wall, and whatever force you exert on the wall is going to be forced back on you as well. So maybe not a good idea, because for every action there's an equal and opposite reaction. Forces always occur in pairs. A single isolated force in nature cannot exist. For every time you create a force, there will be an equal and opposite reaction. So as you create force in the universe, there will be opposite force, so no new net force will be created in the universe. One example, you exert your weight against the earth pushes you back. So whatever you push against the earth, there's a push back. Let's take a look at that more closely. The force exerted by the earth to an object is called weight. So we're going to identify the cause of this, gravity, in a later chapter, but we've already touched on it in the sense of the gravitational acceleration near the surface of the earth. We say weight as a force is equal to your scalar mass times the gravitational acceleration, 9.80 meters per second squared, down towards the center of the earth. So with that acceleration multiplied by your mass, you get the force, which we call weight. That's an F equals ma type equation, Newton's second law. In this case, the acceleration is our value of g, 9.80 meters per second squared. The gravitational acceleration on the moon is 1/6 that of the Earth's acceleration. So if you went to the moon, you would only weigh 1/6 as much, because the acceleration is 1/6. You still have the same mass, but only 1/6 of the weight. So if you were a 180-pound astronaut on the Earth and you travel to the moon, you will only weigh 30 pounds on the moon. I'd like to say that one of one of my fantasies for the future is to be able to take a weekend trip to the moon, go to the moon, and play basketball all weekend. It's because while you're playing basketball, you can jump up and fly around and dunk the ball, because you will have muscles made for a 180-pound person, and then you all of a sudden only weigh 30 pounds. So you'll be able to jump around and do whatever you wish. And just make sure you don't stay too long on the moon, because after a while your muscles will start to atrophy, and that won't be so good. So just want to go for a weekend, play basketball all weekend, come back, recover, go to work, and then look forward to your next time that you can take a trip to the moon and enjoy some basketball. All the old videos of the astronauts, the Apollo astronauts who went to the moon, they're carrying these large backpacks, and those backpacks, when they're on Earth, weighed between 150 and 200 pounds, and they get to the moon and they're just bouncing around on the moon, no problem, because now those backpacks weigh about 30 pounds, and really no problem for them there. So the astronaut's weight is different, but he or she will still have the same mass anywhere they go. So here's our problem-solving strategy. We're going to draw a free body diagram for the object. The free body diagram shows all the external forces acting on the object. Only those forces acting on the object, not the forces that the object exerts on other things, just the ones that are exerted on the object. We'll set up convenient x and y coordinate systems, sum up all the forces in the x direction, positive or negative, along the number line, add those up, set those equal to mass times acceleration in the x direction. Sum up all the forces in the y direction, do that same thing, positive or negatives, add them all up together, set that equal to mass times acceleration in the y direction. Solve these equations for our unknowns, and that will be our basic problem-solving strategy. Let's try this out. A traffic light weighing 125 newtons hangs from a cable fastened to a support. The upper cables make angles of 37 and 53 degrees with the horizontal. Find the tension in the three cables. Alright, so we have a traffic light. The first thing we're going to do is make a free body diagram. So we're going to make a picture of the light and then label all the external forces acting on the light. We got a weight pulling down towards the center of the earth, and we have the tension of the cord pulling up towards the interior of the cord. And that's the way tension works, just as a sidelight. Anytime you've got a cord and you consider any point within the cord, it's in equilibrium, so there's no net force on it, but there is tension, and tension is pulling one way and it's pulling the other way. So at any particular point on a taut cord, you have tension pulling on both ends, giving you a net force of 0. That's the way it is on every point on that cord until you get to the end point. Now on the end, you've got the support pulling one way and the tension in the cord pulling inward on the cord. So the tension is going like this, support's going like this. If you go to the other end of the cord, the support's pulling this way, tension's pulling inward on the cord. So anytime you have a taut cord, the tension on the ends is pulling inward on the cord. And that's the way it's working on this traffic light. We can see the tension is pulling inward on the cord as it's pulling upward on the traffic light. So we have this vector free body diagram, and we're looking at the y direction, and we see that if we sum up all the forces in the y direction, positive or negative, it should add up to 0. And if we define up as positive, then tension 3 is a positive T3, and down is negative, then we have a negative weight going the other way. So we have T3 plus a negative weight equals 0. So in terms of magnitude, tension 3 equals the weight, and we're told that the weight was 125 newtons. So tension 3 is 125 newtons. We want to find the other tensions, so we look upward at where the three chords come together and they're joined together as a knot. And we notice one special thing about this knot. As we look at the knot, we notice that the knot is not moving. So the knot is not moving, and because the knot is not moving, all the forces on it should add up to zero, at least in a vector sense. So we apply Newton's first law in any direction. If we look at the x direction, all the components of forces in the x direction should add up to zero. And we actually have two components in this case. We have a T2 cosine 53 degrees going off in the positive x direction, and we have a T1 cosine 37 degrees going in the negative x direction. So adding these components together, positive and negative, they should add up to zero. We have that tension 1 cosine 37 degrees equals tension 2 cosine 53 degrees. Solve this for tension 1. Tension 1 is the cosine of 53 degrees divided by the cosine of 37 degrees times tension 2. Put in our numbers, we'd say tension 1 is equal to 0.75 tension 2. All right, so we have a relationship between these two tensions. If we look at the other direction, the y direction, we actually have two components that are going in the positive y direction. We have a T2 sine 53 degrees that's going up, and another T1 sine 37 degrees that's also going up. And then we have all of tension 3 pulling down. That's one of the ends of this taut cord, and so at that point the tension is pulling inward on the cord, is pulling down. Alright, so let's bring the T3 over to the left hand side. And so we have T3 is equal to, and the sine of 53 degrees is 0.8, and the sine of 37 degrees is 0.6. So this is our equation right now. T3 we already know is 125 newtons, and T1 we solved in terms of T2 as being 0.75 T2. So now we have this. 125 newtons is equal to 0.8 T2 plus 0.6 times 0.75 T2. And we have one equation now with one unknown. Solving for tension 2, we have tension 2 is equal to 100 newtons. 125 divided by 1.25, 100 newtons. Substituting in for the other force, tension 1 is 0.75 times tension 2, so that is 75 newtons. So notice on this last example that we had tension 3, which was 125 newtons. Tension 1 was 75. Tension 2 is 100. 75 plus 100 is not equal to 125. So you can't linearly add these values of these magnitudes and get the third force. You have to do it vectorially in terms of magnitude and direction in order to add them up and get this third force. All right, let's look at another example. In this case, a cart on a frictionless incline. A cart of mass m is on an icy driveway at an angle of theta. Determine the acceleration of the cart, assuming the incline is frictionless. So we have a cart on an incline, and this cart has wheels, but it's a frictionless incline anyway, so the wheels aren't going to turn. It's going to slide down without friction down this incline. If we were to do a free body diagram, selecting a coordinate system that is convenient with the incline, so we're going to have x going down the incline, y going perpendicular to the incline. I want to look at all the external forces acting on this cart. One force is gravity, mg, pulling down towards the center of the earth. Sounds good. Another force is what we call the normal force, and that is the surface force. It's always perpendicular or normal to the surface that this object is resting on. So in this case, the cart is resting on the incline. Normal to the incline at a 90-degree angle is what we call the surface pushing force, or the normal force. So these are the only two external forces acting on this cart. we really need to have all of our forces cooperate with our x and y directions. The normal force is cooperating. It's totally in the y direction. The mg force is not cooperating. So we need to break it up into its components, x and y. So I'm going to look at this triangle, and the hypotenuse of that triangle is going to be mg. And I want to find out what these components are, one down the incline and one into the incline. Now, if I look at these triangles, look at this big triangle right here, the one that has theta on the incline. If I look at that triangle, that is a right triangle, and with a right angle right here. And that means that this angle up here that I haven't identified is actually, this big angle up here, is 90 minus theta, because they have to be complementary in a right triangle. So I have theta down here, 90 minus theta right here. Now if I look at the small triangle, the red triangle, I have an angle, it's a right triangle as well. It's a similar triangle actually. And I have a 90 minus theta up here with a right angle, and that means that this angle right here has to be theta. The same as theta as the incline itself. So now I know what theta is here, and looking at this right triangle, the small right triangle, I can now identify what my components are. My hypotenuse is mg, and opposite theta should be mg sine theta, and adjacent to theta should be mg cosine theta. So I'm going to have an mg sine theta going down the incline and an mg cosine theta going into the incline, just based on geometry. There's only one force, net force, in the x direction if I do things this way. The normal force and the mg cosine theta are canceling out in the y direction, and I only have one net force in the x direction, and that is mg sine theta, but it's not zero. It's some finite mg sine theta net force, and that's what's causing an acceleration in the x direction. So I would say that sum up all my forces in the x direction, there's just one force, and that should equal ma. So ma is equal to, at least in the x direction, mg sine theta. I can see that I can get rid of an m on both sides. And my acceleration in the x direction is g sine theta. So that is the acceleration of this cart down the incline. Note that this acceleration has no dependence on the mass m, so any cart of any size on this frictionless incline will accelerate down the incline at the same value of acceleration. So if you had a race between different size objects on this incline, they all will go down at the same rate. Also look at this same at the special cases. Maybe I'm confused as to whether this should have been g sine theta or g cosine theta. So one way to check that is to look at the extreme case. Let's say I take my incline and go, let's do it like this. I go all the way down to 0. So theta is 0. What's my acceleration down the incline then? Well, if my incline goes to 0, theta goes to 0, the sine of 0 is 0, and my acceleration would be 0, and this object would not go down the incline. It would be on a flat plane, so there would no longer be an acceleration down the incline. So that makes sense. If theta went to 90 degrees, I should have done that too. Theta goes to 90 degrees, I'm going to a right angle like this, and then now my acceleration will be just the full pull of gravity. So at 90 degrees, my acceleration should equal g, and the sine of 90 degrees is 1, so the acceleration will equal g at that point. So our result here meets these limiting cases, special cases of 0 or 90 degrees, and so I'm pretty sure that g sine theta is the right one rather than g cosine theta. Note in the y direction there is no acceleration. It's static. The two forces are canceling out, giving us a net force of 0. So the normal force should equal mg cosine theta. The summation of all the forces in the y direction will be 0, Newton's first law. And we have the normal force plus a negative mg cosine theta because it's in the opposite, the negative y direction. So the normal force equals mg cosine theta, at least in magnitude. Again, we can check the limiting case on this. If theta went to 90 degrees, cosine of 90 is 0, and this thing will fall like this, and there will be no normal force anymore. There's no contact with the incline really as it's falling like that. So no normal force at 90 degrees. If theta goes to 0 degrees, cosine of 0 is 1, the normal force will equal its weight because the normal will be pushing up, mg will be pulling down, and normal force will equal mg. So at 0 degrees, cosine 0, 1, normal force equals mg. It fits those limiting cases. So 0 at 90 degrees, no normal force. At 0 degrees, normal force equals mg. Let's try an example of a cart coming down this incline. If a cart starts from rest at the top, theta is 20 degrees, length of the incline is 25 meters. How long does it take to travel to the bottom? Well, the acceleration should equal g sine theta. That's 9.8 times the sine of 20 degrees, or 3.35 meters per second squared. So that's our acceleration. We know the length, 25 meters, and we know that we started from rest. So we have 3 kinematic variables that we know. So we can solve this. Our displacement should equal our initial velocity times time, our initial velocity being 0, plus 1/2 acceleration times time squared. So our displacement simply will equal 1/2 acceleration times time squared in this case. Multiply both sides by 2, divide by acceleration, take the square root. So our time will equal 2 delta x over the acceleration square root, 2 times 25 meters over our acceleration of 3.35 meters per second squared, square root. It'll take 3.86 seconds to get to the bottom. What's the cart speed at the bottom? Velocity will equal initial velocity plus acceleration times time, but our initial velocity was 0. So simply acceleration times time in this case. We have 3.35 times 3.86 seconds. We will have a speed of 12.9 meters per second at the bottom. And that's that. We'll leave it at that. So we can see, even though we're dealing with dynamics here and forces are related to acceleration. Once we get acceleration, kinematics can be applied as well. And so kinematics is still an underlying theme with all this in terms of acceleration and the kinematic variables. So we need to keep that in mind as well. So let's stop this lecture there and go on to a little bit more chapter 5 dealing with friction.